In this video, we are going to check the robustness of ArubaOS CX MCLAG, multi-chassis lag, by testing links failure scenarios and see the minimum associated impact on the campus traffic. So let's consider the following topology. We have two clients connected to the same access switch Aruba 2930F. This edge switch is connected with a link aggregation terminated on two 8400 Aruba chassis, acting as layer 2 and layer 3 aggregation nodes. Client will initiate traffic to a test server connected behind core switches, core 3 and core 4. Aggregation switches are interconnected with link aggregation 1, lag 1, which is the inter-switch link for VSX MCLAG. A keep alive mechanism based on UDP packets sent over the direct layer 3 link protects the VSX stack against split brain. Layer 3 VLAN interfaces, here this is interfaces for VLAN 10, are configured on each active nodes that advertise the client subnet, so 10.10.10.0/24, to upstream core switches through OSPF. Let's have a look now at the nominal situation with some ICMP flows that we will start from client 1 and client 2 to the test server. So we are going to issue pings with a timeout of 10 milliseconds. So the traffic impact we are going to analyze will be the number of lost packets times 10 milliseconds. So the first test would be the failure of a link between the access switch and the distribution layer. And the second test would be the failure of the ISL links, and see how the keep alive will protect that split brain and make sure that the traffic is impacted with a very minimum downtime. So let's now go through some show commands to verify the topology. So this is the topology in the middle of the screen. Let's put the CLI of 8400-1 on the left, and similarly 8400-2 on the right. So I'm going to do a show LLDP neighbor. You will see that there are actually one is shown on the picture, but two access switches are connected. I've got connection to core 3 through interface 138. That's for upstream routing. I've got a lag connection that would be through 181 and 131, and similarly to the other box. And let's do on the second switch the same type of LLDP information to get the topology. Now let's do a show MCLAG brief. That's going to provide me a few information. First, the ISL state is in sync, fully synchronized. So let's do the same on the second box. I've got the role that is a secondary role on the left and a primary role on the right due to the MCLAG priority that has been set. Then I know that the keep alive is fully established, so the keep alive UDP packets. I can do now a show MCLAG status to give you the verification that lag 1 that I'm going to shut in test 2 is the ISL port. Finally, I can do a show LACP interfaces multi-chassis to provide you information about the LACP multi-chassis across the two chassis and have the full visibility, local and remote peer. So show LACP interface multi-chassis on the second one. So you'll see here the actor detailed, which is the local one, so the box on the left, the partner, which is the 2930 on port 25 connected to 111, and then I've got very interesting information about the remote actor, so the peer 8400 neighbor that has 111 connected to port 26. So that's about the second link to the 8400-2. Finally, let's have a look on the edge switch, the 2930, to see the topology, show LLDP information remote, to see the two distribution switches that are connected to port 25 and 26. And if I do a show LSCP, I'll see that LSCP is active, and everything is up and successfully forwarding. Let's load now topology with the ICMP flows that are from the client 1 and client 2 up to the test server. So on the left top side, I've got my VMware console to the machines that I'm going to issue the ping. And on the right side, I've got the access switch on which I will look at the counter for bytes being received and transmit. So let's clear again the statistic, then show on interface 25 what are the bytes being received and transmit, and for interface 26 about the same. So you'll see there is very few bytes being transmitted and sent. Now I'm going to load that with 1000 packets per second. So let's load with one flow and see what are the resulting transmit. So you see that on port 25, I'm transmitting a lot of packet and receiving almost none of that traffic. So let's see on 26. On 26, this is the reverse. So I'm receiving a lot of traffic. So this is just to show you the traffic asymmetry. So I'm really transmitting on 25 and receiving traffic on 26. So this is why I'm using a second client to perform the same with a difference in terms of IP address being .12 instead of .11. So I will use the hashing mechanism to load balance across the two links. So let's go to the second source of traffic, pinging to the same test server at the very top. And let's see now what is the effect of that. So I can clear the statistic again and go to interface 25. And you see now that interface 25 is equally loaded RX and TX. And now the same for 26 and the same. So now I can make sure that if I shut down port 25, the link going to port 25 or the one going to 26, I will equally impact the network. So it's time now to perform our first test. So let's shut down the circuits between 8400-1 on the left to the access switch. So for that, this is 111 port and shut. So I can clear again the statistic here to see if I'm receiving something on 26. Still on 26, and on 25 I'm receiving nothing. Okay, so I can now stop the ping. On the first unit you can see that I have 13 packet being lost. So the difference between the transmitted packet and the received packet. And on the second one I've got one packet being lost. So the impact was actually that on second Linux station. So that was 13 packets. So that's 130 milliseconds. So that was 13 packets times 10 milliseconds. So 130 milliseconds in terms of downtime. So let's see now what is the impact if I put back the circuit. So I'm starting the ping. And I'm going to restore the link. Now let's see if I receive something on port 25. Yes, I'm receiving. So now let's close the ping. So I lost 5 packets. Here I lost 4 packets. So that was 5 packets being lost, so that's a maximum of 50 milliseconds. So a total of, again, 130 milliseconds for a link being down, and restore took 50 milliseconds. So very, very minimum downtime. You can see that MCLAG is perfectly behaving as expected for downlinks failure up to the access switch.